तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we worked out several examples illustrating the application of the Laplace transform technique to the solution of transients in networks. We also made a special mention of the particular virtues that Laplace transform technique brings to the solution of such problems. We compared the Laplace transform method with the differential equation approach and pointed out the various benefits, benefits that the Laplace transform technique will bring in. We also made a note that where the initial conditions are specified at different points of time, not necessarily all at t equals 0, the differential equation approach will be probably more beneficial than the Laplace transform technique, because there is no provision in the Laplace transform technique to take care of specification of conditions at different points of time. If you have such a situation, then you once again end up in arbitrary constants even with the Laplace transform solution, so there is no special advantage in that. Today we will start with another example of a network transient problem in which a discontinuous source is present, and then later on we move to a discussion of the application of the Laplace transform technique to a general system. So let this be a voltage source Vs included in a circuit of this type, the capacitance of 2 farads and a DC source of 4 volts. And this Vs is a discontinuous source having 1 volt, a pulse lasting from 0 to 1 second. And we will also assume that steady conditions are reached at t equals 0 minus with Vs equals 0. So before the pulse is switched on, Vs is of course 0, and at that time we assume that the steady state conditions are reached. The question that is asked is find Vct for t greater than or equal to 0. This is the question that is asked. Now we set up the transform diagram for this. Before doing that, we need to know, because there is one reactive element, the capacitor, we should like to know the 0 minus value of the capacitor voltage. So to do that, let us see the system, the various parameters in the system at various variables in the system at t equals 0 minus. At t equals 0 minus, this voltage source is 0. You have a 1 ohm resistance, a capacitor, another 1 ohm resistance, and a DC source. This is 4 volts, this is 1 ohm, this is 1 ohm, and this is a capacitor of 2 farads. So obviously, if the steady state conditions have been reached in the circuit, this 4 volts will drive a current of 2 amperes through the 2 1 ohm resistors in series, and there will be a 2 volts developed across the capacitor. Therefore, Vc0 minus is 2 volts. So that is the voltage initial condition of the capacitor that we have to use in solving this problem. So let us form the transform diagram of this. Transform diagram of this would be, for the voltage source, you have the Laplace transform of this voltage source. This is ut minus u of t minus 1 is a pulse function. Therefore, the Laplace transform of this will be 1 by s times 1 minus e to the power of minus s. That is the voltage source. In addition, we have this resistance, another resistance 1 ohm, and then a capacitance whose impedance is, generalized impedance is 1 over 2s, and then a source representing the initial capacitor voltage. This is a 2 volt source, therefore this will be 2 upon s, and then you have the Laplace transform of this DC voltage source, which is 4 upon s. Now the capacitor voltage is what is required. So it is the voltage across these two nodes. This is Vc of s. As pointed out in the last lecture, when you are interested in finding the capacitor voltage, you should not try to measure the capacitor voltage across this portion only, because it is the totality of these two together is what represents this 2 farad capacitor, including the initial condition source. So when you want the capacitor voltage, it is the voltage between these 2 points which has to be calculated. Now, a simple way of solving for this would be to take the node equation approach, take this as the datum node, and call this 1, this as 2, this as the 3, and perhaps this as 4. And therefore, if you find out the voltage of node 1, that will yield you the capacitor voltage, which is the voltage, of course, with reference to the datum node, node 1 with reference to the datum node. So writing the node equation at node 1, Vc of s times the sum of the admittances connected to this node, 1 plus 1 plus 2s minus the coupling terms with reference to the voltages of the other nodes. So with reference to node 2, we have 1 by s times 1 minus e to the power of minus s. That is the voltage of node 2, and the coupling admittance between nodes 1 and 2 is 1, therefore times 1, minus node 3 has a voltage 4 upon s, and the admittance of the element connecting nodes 1 and 3 is 1 times 1, minus node 4 has a Laplace transformed voltage 2 upon s, and the admittance between 1 and 4 is 2s, generalized admittance, equals 0. So if you, all the terms here are known except Vc of s, so if you transfer these quantities on the other side and find out an expression for Vc of s, it turns out to be 2 upon s plus 1 over 2s times s plus 1 times 1 minus e to the power of minus s. That is what it will be. So you can write this as 2 upon s and make the partial fraction expansion of this portion only, because later on we'll interpret this 1 minus e to the power of minus s, how it reflects in the time domain. So we'll make the partial fraction expansion of this only. That will be consisting of 2 terms, half and minus half times 1 minus e to the power of minus s. So essentially, therefore, you have 3 quantities to deal with. 2 upon s is 1, plus half upon s plus minus half upon s plus 1. That is one group of terms, and the same group of terms multiplied by e to the power of minus s. So if you find the inverse Laplace transform of each one of these groups and add them up, that will be your Vc of t. So Vc of t would be, this will be 2 times ut. Here you have half ut minus e to the power of minus t ut. That is the inverse Laplace transform of this. and you observe that this is the same thing as this, except it's multiplied by e to the power of minus s, which means whatever time function we have here is delayed by 1 second. That's all it means. Therefore, this is minus half of u of t minus 1 minus e of minus t minus 1 u of t minus 1. So that is what it would be. You can sketch this Vc of t. So Vc of t would be, this 2ut will be a step function like this. This is 2 times u of t, and this is ut minus e to the power of minus t ut. So start with it is 0 and exponentially climbs to a value equal to half. So this is half of ut minus e to the power of minus t ut. That is what it will be. As far as this portion is concerned, it has a negative value, it is a negative of this, but it starts from t equals 1. Therefore, it will be something like this and asymptotically reaches half. So if you add all these, you will get some curve comes like this and then it decays to it. These two will add up to 0 ultimately. Like this. So this is your total solution. So that is Vc of t. So this problem illustrates how you can handle the solution when there is a discontinuous time function, and how the discontinuities or a time function is, of course this is discontinuous, and how when finding out the inverse Laplace transform, when you have e to the power of minus s or such terms are present, how you can find out the inverse Laplace transform, making use of the property that e to the power of minus s means that that particular function of time is delayed by 1 second. If it is e to the power of minus ts, it is delayed by t second. To discuss the application of Laplace transform technique to a general system, let us consider a system represented by this black box. This is a linear, time invariant, continuous time system with an input xt and an output yt. We shall assume that all initial conditions are 0. That is, the output response quantity yt and all its derivatives are 0 prior to the application of the input xt. We will also assume that xt is causal. That means x of t is identically 0 for t less than 0. Now, we have taken a single input, single output system, and if there are really a number of inputs, multiple outputs, we can find out the response to each of the individual inputs in turn and use the superposition principle. Therefore, there is no laws of generality involved in our taking a single input, single output system. We have seen that such a linear time invariant continuous time system is in general described by a differential equation of the type an dnx dtn plus an minus 1 the n minus 1th derivative of, this should be y, output quantity y, dny dtn, dn minus 1y dtn minus 1 on up to a naught y equals dmx dtm plus dm minus 1x dtm minus 1. We have a coefficient dm minus 1 here. dm minus 1 x by dtm minus 1 up to b naught x. This is an nth order differential equation with constant coefficients. Now, we assume that yt and all derivatives are 0 for t equals 0 minus and of course t less than 0. That means it's identically the circuit is dead as far as the response quantity is concerned, and so is xt, because xt is a causal function is identically 0 for all negative values of time. So under these assumptions, we can take the Laplace transform of all the terms on the left hand side and right hand side. In doing so, since all the initial conditions are 0, if the Laplace transform of y is y of s, the Laplace transform of dn y dtn is simply s to the power of n times y of s. So that makes the transforming this equation a very simple task. So if you take the Laplace transform of that, you have a n s to the power of n plus a n minus 1 s to the power of n minus 1 times a naught plus a naught times y of s equals the Laplace transform of this side of the equation, which is s to the power of m plus a bm minus 1 s to the power of m minus 1 on up to b naught multiplying x of s. So that is the differential equation after transforming its after making the Laplace transform of the differential equation. It is converted in algebraic equation, transforming, relating the transform of the response quantity to the transform of the input quantity. Now the ratio of y of s to x of s is therefore the ratio of two polynomials, s to the power of m bm minus 1 s to the power of m minus 1 plus b naught divided by an s to the power of n an minus 1 s to the power of n minus 1 c naught. This we can put ratio of two polynomials g of s over f of s. Now I have taken the leading coefficient here to be 1. It doesn't entail any laws of generality, because even if there was a leading coefficient here which is different from 1, we can divide all the terms by that term and make this reduce to 1. Therefore, there is no laws of generality involved in taking this leading coefficient here to be equal to 1. Now this y of s or h of s, x of s in this derived in this fashion is called h of s, the system function. So formally we can say the system function h of s is the Laplace transform of the output quantity y of t by the Laplace transform of the input quantity x of t with 0 initial conditions. What we mean by 0 initial conditions is that the response quantity and all its derivatives are going to be 0 at 0 minus, and before the application of the input xt. So in this particular case, we have taken xt to be a causal function which is identically 0 up to t equals 0 minus, and then until that time the response quantity and all its derivatives are going to be 0. Therefore each of these, when it's transformed into Laplace transform domain, dn y dtn goes as simply s to the power of n times y of s. This system function is also referred to as transfer function in literature. Particularly in the context of networks, control systems and so on, this is also referred to as transfer function. Another name for this. So essentially, when we talk about a system function in the Laplace transform situation like this, we are saying that is the ratio of the Laplace transform of the response quantity, the Laplace transform of the input quantity with 0 initial conditions prior to the application of the input. You recall that earlier we said in the introductory lectures that system function is the ratio of the forced response of the system to the input when the input is of an exponential signal. In other words, the earlier definition was HFS was defined as the forced response YF of t to an input of the form e to the power of st. So we said at that time that if you had a system for which you have an input est and then that is xt is equal to this, then the output, the forced response output will be HFS times e to the power of st. Now we have defined the system function in a different way. Are they the same? So we would like to now analyze this and then tie them up and see, we want to show that both of them are indeed the same. Now how do we go about it? We know that x of t from the Laplace transformation theory is related to x of s by 1 over 2 pi j c minus j infinity to c plus j infinity of x of s e power st ds. What it means is limit as delta omega goes to 0 of summation of elementary signals x of s times delta omega over 2 pi. X of s is the coefficient density, x of s times delta omega over 2 pi is the coefficient of a signal of this type e power st. Summation over all such signals will yield xt. And how do we take these elementary components? You take the Bromwich contour here and take any particular complex frequency Si and then take a width delta omega, and then if you take the exponential signals corresponding to each such element, that will add up to this. In other words, we can write here x Si of t, where Si is one particular frequency and summed up on I. So if this is the situation, then we can think of any arbitrary input xt as the sum of exponential signals of this type. So let us see how it goes. Suppose we have the input and the forced response. So if the input has been e power sit, according to our earlier discussion, the forced response will be hsi e power sit. Now on the other hand, we have now not a single si of t, but a whole lot of these si of t, each weighted by a coefficient like this. Therefore, if I have x si delta omega over 2 pi e power sit, that would give me, by linearity principle, because it's a linear system, you have hsi x of si delta omega over 2 pi e power sit. Now this is one particular complex frequency signal with a tiny amplitude like this. Now we have a whole lot of these complex frequency signals, therefore we take the sum on I, x si delta omega over 2 pi e power sit, that should give me correspondingly limit as delta omega goes to 0 of x si delta omega over 2 pi e power sit. This of course also on limit as delta omega goes to 0. And this is exactly what xt would be. Xt we have seen from the Laplace transform theory is limit that delta omega goes to 0 of x si delta omega over 2 I e power sit. So all these tiny exponential signals ranging from minus infinity to plus infinity along this Bromwich contour, if you add all of them, that will fetch you x of t. That means this is really x of t. So if you have this x of t, and the combination of all such signals can be put in the integral form 1 over 2 pi j c minus j infinity to c plus j infinity of, now s is a running variable, no longer discrete values, x of s times x of s e power st ds, because ds is j times delta omega. So this is what it will be. So from this we have observed, if you take this entire quantity, if you call that yf of t, this yf of t has 1 over 2 pi j c minus j infinity, c plus j infinity x of s, h of s, xs e to the power of st ds. That means the Laplace transform of f of t will be xs, hs times xs. That means we have yf s Laplace transform is hs times xs. So according to our earlier definition, we found that the sum of the forced responses will have a Laplace transform which is h of s times x of s. But in our Laplace transform theory, we are saying the total response y of s is equal to h of s times x of s. So is it that the total response yt is the same as yf of t that we have got obtained here? The answer to this is that they turn out to be the same, because this Laplace transform, inverse Laplace transform integral, provided you take s in the region of convergence of the transform h of s times x of s, it turns out from the Laplace transform theory that if you plot yf of t, this is going to be identically 0 for negative values of time, and it may have some other value like this for t greater than 0. This is yf of t. So according to the Laplace transform theory, yf of t is going to be identically 0 for negative values of t, and it will have only values for positive value, non-zero values for only positive values of t. And in our system, we also have yt, which is identically 0 for negative values of time. Therefore, yt agrees with yf of t identically for negative values of time. Therefore, there cannot be any other term if it is introduced that will spoil the initial conditions of the problem. Therefore, this yf of t is also equal to yt. Consequently, there cannot be any other extra term that is present. So this yf of t is indeed equal to yt. Therefore, yf of s, which is hs times xs, is indeed the same as ys xs times hfs. Therefore, yf of s obtained in this fashion is the same as y of t. So the discussion therefore gives us this information that the sum of the forced responses calculated in this manner will also yield the total response. Total response in the sense there cannot be any other term as far as the negative values of time is concerned. But as far as positive t is concerned, this whatever you calculate for yf of t will include the finite number of transient terms and the finite number of forced frequency terms appropriate to the given hfs and xfs. There are finite numbers, and in the conventional sense what we talk about, what we mean by transient terms, transient response and forced response pertaining to xt and ht as far as t greater than or equal to 0 will always be obtained in yf of t. Even though we are calling this forced response yf of t includes the transients and the steady state responses that emanate from t equals 0 onwards. The reason why we are saying this forced response, because all these tiny exponentials here start from minus infinity onwards. So they are all starting from minus infinity. All these exponentials are starting, and each of them produce a forced response, and the sum of those forced responses agrees with the total solution for negative values of time. That means there cannot be any other additional terms starting from t equals minus infinity onwards. But yf of t, which is obtained here, as far as this part of the solution is concerned, it includes both the transient and steady state terms, which we talk about in a conventional fashion. So hfs that was defined earlier and hfs that we have defined now are one and the same. Therefore, we don't have to make any distinction between these two. And this hfs plays a very important role in system studies. It has got various useful properties and various interesting properties, and it will be our task now to take up a discussion of the various important aspects of the system function hfs, and that we will take up next. So this system function HFS has many important connotations. So it will be our task now to look at these connotations. So let us say it has many facets to this system function HFS, and that's what we would like to study. So we are talking about a linear time invariant continuous time system with an input xt and an output yt, and the system function enables us to relate the output to the input not by means of a differential equation which is complicated, but by a simple algebraic equation in the Laplace transform domain. We also assume here that zero initial conditions. That is important. So once we have the zero initial conditions, the output and input are related by a pure algebraic equation where HFS is in general a rational function, a ratio of two polynomials. And that differential equation is converted to an algebraic equation of this type is the central advantage of the transform technique, of which Laplace transform is a very prominent technique. Now let us look at the various aspects. A. Suppose we have impulse input. A special case, not a general x of t, but let us say we have an impulse input. So what we are talking about here is input is delta t, and you get an output which perhaps varies like this. We will call that h of t. So corresponding to an impulse input, impulse at the origin, you get an output h of t. H of t is called the impulse response, which already we observed earlier. Now applying this formula here, y of s, whatever output you get here, is related to the input by this manner h of s, the system function, times x of s. X of s happens to be 1 because xt happens to be delta t, x of s has 1. The Laplace transform of delta t, as we know, equals 1. So that means the output is simply h of s, but that output we are calling h of t. Therefore, Laplace transform, or I will write this y of s itself is h of s. So the inverse Laplace transform of y of s, which in our particular case is h of t, is the inverse Laplace transform of h of s. In other words, the impulse response ht and the system function form a Laplace transform pair, and it is in anticipation of that we use the symbol h for the impulse response and capital H for the system function. So this is a very important result. The system function h of s is the Laplace transform of an impulse response. That means you apply a unit impulse to the system with zero initial conditions, unit impulse stationed at t equals 0. Whatever response you get, we call that h of t. That will be the inverse Laplace transform of h of s. Or if you know impulse response h of t, you can find out h of s by taking the Laplace transform of ht. These two form a Laplace transform pair. Now using this information, general solution in time domain, general input xt, suppose you are having, and you want to find out the output in time domain, we know that y of s equals h of s times x s of s. Now by the convolution property, we know if y of s is the product of two quantities h of s and x of s, then yt we know is the convolution of the time domain quantities which are the inverse Laplace transforms of these two. The inverse Laplace transform of h of s is ht. The inverse Laplace transform of x of s is your xt. So in other words, the output is the convolution of the impulse response and the input quantity, which a fact which we already observed in our preliminary discussion. We already noted this. I'm just trying to relate this to the Laplace transform equation in this manner. What does it mean? This is the convolution integral. It means 0 to t h of t minus tau x tau d tau. Alternately, if you wish, you can write as 0 to t h tau x of t minus tau d tau. These are, because this you can interchange the roles of these, both these are equivalent to each other. And as I mentioned earlier on, if it may turn out that x of t may have impulses at the origin, h of t may have impulses at the origin. So to take care of those impulses at the origin, in general it would be advisable to take the 0 minus to t plus, 0 minus to t plus, if to take care of the possibility that xt or ht may have impulses at the origin. If they don't have impulses at the origin, it doesn't matter whether you take 0 to t or 0 plus or 0 minus. Now these integrals are called convolution integrals. They are also called in literature superposition integrals, because after all you are superposing the effect of x of t by treating them as a variety of, as a summation of different impulses, something which we have already discussed. So the significance of this convolution integral as a superposition of the input considered as a sum of impulses is something which we have already discussed. A third aspect, I also mentioned in our earlier discussion that step response is also a way of characterizing a linear system. So let us see how it is related to your system function HFS. So in step response, we are thinking of a unit step applied as the input. So xt is ut, and the corresponding output, whatever you are having here, is given a special symbol at. And this at is called the step response. Sometimes it is called indicial response. Now using this general equation, ys equals hs times x of s. So in our particular case, this is h of s, and x of s happens to be 1 over s, because the Laplace transform of a unit step is 1 over s. And y of s, the particular Laplace transform of the step response that we are getting, let us call that a of s. That means if at has for its Laplace transform a of s, capital A of s, then a of s is hs times 1 over s, or h of s equals s times a of s. So the relation between Laplace transform of the step response and the Laplace transform of the impulse response is given like this: h of s times 1 over s is a of s, or s times h is equal to h of s. Now using this step response, let us see how we can find out the response to a general input. Response to a general input xt in terms of step response. Now if x of t is the general input, ys will be hs times x of s is the fundamental rule that we are having. But h of s is s times a of s, so I can write this as s times a of s times x of s. That's what we are having. I can write this as s times x of s times a of s. Now y of s therefore is the product of two Laplace transforms, s times x of s and a of s. The time function corresponding to this is the indicial response at. What is the time function corresponding to this is dx by dt, the derivative of this, taking into account that starting from t equals 0 minus. Therefore, yt can be written as x prime t. When you take the derivative of x prime t starting from t 0 minus, that is, if xt is like this, this is x0 minus, this is x0 plus. When you are taking the derivative, you must take this transition also into account. And that is the meaning of this. X prime t considered from t equals 0 minus onwards, convolved with a of t, which is the inverse Laplace transform of that. Now you note that x prime t, if this is the variation of x of t, this is xt, x prime t can be written as, in the jump 0, x0 minus is 0 because we always talk about causal inputs. So the causal input 0 is jumped to 0 plus. Therefore, the derivative you get x0 plus times delta t plus the rest of the derivative taking starting from t equals 0 onwards, 0 plus onwards. So x prime t starting from t equals 0 minus can be thought of as an impulse function which comes because of this jump plus the derivative from t equals 0 onwards. So I can write this further as x0 plus times delta t, this convolved with at, plus x prime t, which we consider only from 0 plus onwards, convolved with at. That is what we are having. And we earlier observed that any function of time convolved with delta t means is equal to the same function itself. Convolving with delta t doesn't change the function. Therefore, I can write this as x0 plus times at. This you can also visualize easily because the Laplace transform of delta t is 1, the Laplace transform of this is a of s, then the convolution as a Laplace transform 1 times a of s, the inverse Laplace transform gives us back a of t, plus x prime t for t greater than or equal to 0 plus convolved with at. So this is the result that we get. Now let me put this down in the form of integrals more explicitly. So what we have here is yt therefore is x0 plus times at plus this one I will put in the form of an integral starting from 0 plus to t x prime tau a t minus tau d tau. That's what you have. That is the meaning of that. That means your response to any arbitrary input xt can be obtained if you know the initial response or the step response. You can find it out in this manner. This comes from, of course, from this Laplace transform SAS times x of s. Now one can also alternately let us have some, first of all, before that, the physical meaning of that. I will just briefly outline without spending too much time on that. Suppose this is x of t. You can think of this x of t as a step function to start with. This is x0 plus times u of t plus a number of small steps occurring later on at different values of time. And each of these steps will have something related to x tau, delta tau, something like that it will be there. So we have the given x of t can be decomposed as a number of steps starting with x0 plus ut, and subsequent steps will have a height depending on the derivative and the interval that you are taking. So each one of those x prime t delta tau is the height of the step, and that occurs at a point tau. Therefore, it brings forth a delayed step response. So summation of all those things will be represented by this integral, and the response to the initial step is represented by this term. So that is the physical significance of this particular formulation of the output in terms of the initial response. So this is the physical significance of this. Now, if there are impulses in the step response at the origin, suppose A of t has an impulse at the origin, to take that into account, you can put this as t plus to take into account impulses. Maybe I'll write this separately, because instead of reflecting the picture, you can say upper limit taken as t plus to include impulses at the origin, if any, in AT. So it is possible that the step response may include an impulse at the origin. To take that complete impulse into account, the upper limit is taken as t plus. An alternative version after all, I associated this S with x of s. I could have taken associated S with AS instead of x. So it means I could have written xs times S times A of s. So an alternative version would be yt will be A0 plus times x of t plus 0 plus to t plus A prime tau x of t minus tau d tau. So that is an alternative way of representing this, because after all xs is symmetrical in AS and xs. So whatever role xt plays here, AT can also play here. So these are alternatives. Now these two integrals what we have here are also referred to as superposition integrals in literature. They are also referred to as Duhamel's integrals. So these are alternative names for that. Even the convolution integral in terms of impulse response is also called superposition integral, but in literature this is also called superposition integral. These are all superposition integrals or Duhamel's integrals. Duhamel's integral is of course particularly with reference to the step function. Another property of the system function that we would like to make a note of is the significance and poles and zeros of HFS. So HFS is a rational function, as I mentioned, is a ratio of two polynomials. Therefore, it is ratio of GS over FFS. So it is in general there is a constant multiplying factor and product of several such factors summed on I, and in the denominator we have products of such factors summed on I. And the set Zi are called the zeros of this HFS, and the set of Pi values are called the poles of this, something which I think I've already mentioned. So HFS is uniquely specified by the locations of zeros and poles as well as the constant multiplying factor m. So the poles and zeros are generally represented in the complex plane by the Z locations. The Zi locations are indicated by zeros, pole locations by crosses. And it has to be kept in mind that since GFS and FFS are polynomials with real coefficients of s, whenever a complex pole occurs, its conjugate also must be present. Similarly, a complex zero is always accompanied by its conjugate. That means complex zeros and poles occur in conjugate pairs, not singly. As far as the real poles and zeros are concerned, there is no problem. It can appear with unit multiplicity. Now, an important factor that one would notice in solving a system is, suppose you have different types of outputs that you are looking for, and naturally you have different system functions relating the different outputs to the corresponding input. It turns out that suppose you have h1 of s, h2 of s, h3 of s, depending upon the y's that you are talking about, y1, y2, y3, all of them have got the same f of s in the denominator. So f of s equals 0 is what is called the characteristic equation of the system. This is a characteristic of the system. So no matter what response quantity you are looking for, the denominator here, f of s, is the same for all transfer functions, for all system functions, for a given system. This is called the characteristic function equation. And when you talk about y of s here, your h of s times x of s, and you make the partial fraction expansion of this in y of s, then the partial fraction expansion of y of s will involve terms containing poles of h of s, terms involving poles of x of s. In the partial fraction expansion, what you have is terms containing poles of h of s are represent the natural frequencies of the system. They are the PIs here. They are the roots of the characteristic equation. So the natural frequencies of the system are the roots of the characteristic equation. When I talk about natural frequencies, I'm talking about frequencies in the complex domain. They are the they are the roots of the characteristic equation. They are the poles PI. On the other hand, your the terms containing poles of h of s, x of s are the forced frequencies. They are the frequencies that come as a result of the particular input. So when you got y of s, when you make the partial fraction expansion, you get some terms corresponding to the poles of h of s, some terms corresponding to the poles of x of s. The terms corresponding to the poles of x of s, if you add up the time domain response of all of them, this is the forced response. On the other hand, if you take into account only the poles of h of s, they represent the natural frequencies. So the summation of all the corresponding time domain expressions represents the natural response of the system. And the total response is what you obtain when you take the inverse Laplace transform of this. So whenever you want to segregate the total response, its natural response and forced response, you can always look at this as emanating respectively from the poles of h of s and the poles of x of s respectively. As far as the zeros are concerned, they don't have any particular connotation like this. They only vary the amplitude of these various components. Suppose I have one particular response quantity is e to the power of st a. It is the amplitude or the multiplying factor of the complex frequency term that is dictated by the zeros. The poles, however, represent the modes, the time expressions, the complex frequencies that are dictated by the poles, whereas the zeros will only vary the amplitude of the various terms. So in this lecture, what we have done so far is acquainted ourselves with the definition of the system function in terms of the Laplace transforms. You recall that system function is defined as the Laplace transform of the response quantity to the Laplace transform of the excitation quantity with zero initial conditions prior to the application of the input. And the system function in general is a ratio of two polynomials for the type of system that we are talking about, lumped parameter systems, which is f of s, g of s over f of s. And we looked at various properties of the system function. The system function is the Laplace transform of the impulse response. We also saw the system function is also related to the Laplace transform of the step response. We saw the various types of convolution integrals, how to get the general output for the general input in terms of the impulse response h of t or the step response a of t. We also finally looked at the nature of h of s as a ratio of two polynomials which specify the locations of zeros and poles in the complex plane, and we mentioned that the poles of the h of s indicate the natural frequencies of the system. They are invariant for a particular system, and whatever the type of output that you are looking for in that system, they do not depend upon the input quantity. On the other hand, x of s will have some poles which are characteristic of the particular excitation function that you have dealing with at the point of time. So y of s, which is the product of h of s times x of s, will have poles partly coming from h of s and partly coming from x of s. The poles coming from h of s represent the natural frequencies, and the associated response is a natural response. The poles coming from x of s are the forced frequencies, and the associated time response is the forced response. More about the system function will be taken up in the next lecture.